Hey, welcome guys. I am going to do a review of the Unit 1 test. Okay, I'm just going to work through it and try to explain it as I go. So, this was your practice test. Okay, let's take a look here. All right, so this first question is asking about table shows whether students in introductory an introductory statistics class are male, female, and if they play an instrument. So here's the genders, male and female. Here's if they play an instrument, yes or no. Okay. And I think this one actually was a small mistake. I'll fix that in my master copy. So 82. Okay. So the first question that comes up is what is the marginal distribution in percent of gender? So because it's about gender, okay, I care about the numbers down here. The marginal distributions are your outside edge. Okay, so the numbers that are down here and here. Okay, just like on this side, the marginal distribution over here is for the margins for if they play an instrument. All right? So because it's talking about the percentage is how you make a fraction, turn it into a decimal, turn it into a percentage. So what I'm going to do is take 57 divided by 98, which in a calculator gives you about 58%. And then similar for 41 over 98. That should give you about 42%. Okay, so it would be something along the lines of the marginal distribution of gender is about 58% female and 42% male, respectively. Okay, something like that. It was asking about the marginal distribution percent of people that play an instrument. It would be 16% or 16 over 98, which is probably about 17, 18%. Yes, and 2 out of 90. Okay. All right. Let's see here. We have what is the conditional distribution in percent of yes plays an instrument for only male students. So because we're only looking at male students, okay, and it says percent for yes plays an instrument, we're just going to do 7 divided by 41, which I believe is like 0.17 something, so we're holding about 17%. Okay, so we have 17%, so it would be 17% of male students plays an instrument. Right? What kind of display would you use to examine the association between gender and plays an instrument? Just name a type of graph. So there's a bunch of different graphs out there. The ones that work for this would be things like pie charts. You can use bar graphs. Or I think segmented bar graphs would work great with this. Okay. So there's probably better answers. Okay, segmented bar graphs probably the best answer. Pie charts also work. Okay, or pie graphs they call them sometimes, or circle graphs, circle charts. Bar graphs would be okay, but they could still be used. But the best one would probably be segmented bar graphs or pie charts. Does the data show that playing an instrument is dependent on being male or female? Since we're comparing males and females, we have to go through and do these percentages. So 7 out of 41 would be 17%. This would be 34 out of 41. Should be the opposite, which would be about 83%. These combined, 41 out of 41 would be 100%. Likewise, that's 100%. This one is going to be 9 over 57. 48. Nine divided by 57 we get about 16%, 15.7, let's call it 60. That would make this 80. Okay. Once again, I rounded, but it's okay for something like this. If numbers, if I was trying to be more precise, obviously I'd do 1, 2, 3 decimal places. But for now, I think with a problem like this, it'd be okay to round to a whole number. Okay. But does the data show that playing an instrument is dependent on being male or female? Give statistical evidence to support your conclusion. So I would compare these numbers. Okay. 16 to 17, 84 to 83. Now these numbers, the general rule for right now is we're trying to see if they're close within 5 percentage points. Now these are within like 1 percentage point, so they are close. So if they are almost the same, we say they're independent. Okay, meaning it doesn't matter if you're a boy or a girl, the same percentages or close to the same percentages seem to play an instrument. So there's no real like, it's not like, oh, only girls play an instrument, oh, only boys play an instrument. Matter. It's independent. Doesn't matter if you're a boy or a girl. So if they're like the same, independent. So we would say, now we don't know for sure, but the data suggests it. Data suggests males and females or females and males. Data suggests that females and males play instruments roughly same. I'm going to put they said females and males say 60. So independent. Independent. If these numbers were, let's say, 26% and 17%, right? If these were off, that would make these be off also. Therefore, you would say the data suggests that they are not the same, and so they would be dependent. Okay, next question. Number of pizzas that are ordered. There's two things that are happening with this, right? There is a what's called a scale and a shift. So when you're changing the scales, okay, when you're changing it, the scale. So this is number of pizzas. So like one pizza, for example, what would that be? How much would that cost? One pizza cost $12. That's what this, right? $12 per pizza. So all of these apply a scale to, like everything by these. So, for example, instead of saying one pizza, you would say $12. Instead of saying two pizzas, it would be $24. We're changing the scale from the amount of pizzas to the cost for those pizzas. Now, a few things of note, the IQR, difference between your quartile 3, quartile 1, 3 and quartile 3, 1, we're going to do 3 minus 2. So our IQR is just 1, and then 1. So, since this place only delivers pizzas, this is a $4 delivery charge. So everything with the exception of these two is going to be applied that gift of $4 delivery fee. And we are going to skip the IQR and station. And those numbers are considered a spread of your data. Like those numbers, IQR of 1 is not like one pizza, the middle number. No, it's like difference in your quartiles. And with standard deviation tells you have your average plus or minus a little bit. That is, shift that. Data, the space between the numbers won't change. They're just all going up by $4 time. Gap between. So by doing this, I'll do these ones last. Let's go ahead and 1 times 16, 28, 40, 140 per 8. Remember, the IQR is the difference between those quartile 3 and quartile 1. So the same thing, 40 minus 28, 12, which goes back to we don't add 4 to it. Well, these two here, if I have my math, 2656. And I get this by multiplying by 12 and adding 4. Multiplying. So everything but the standard deviation and IQR, those are your spread type numbers. They get scaled, but you don't do the. All right, next question. Home prices around Atterberg, okay, my town. Fucking that smack. All right, so you have summary statistics here. So minimum through your maximum plus your mean and standard deviation. So were any of the home prices outliers, explain how you make a decision. So dealing with outliers with data like this, the median and the mean are way different numbers, 345 and 417. These are home prices. So 345,000 is the median middle number, but the mean is pushed all the way to 400 and almost 1,000. Almost a $70,000 difference between home prices and mean because something weird going on, big skew. So they want to know if there's any outliers, particularly is that number. So to do that, we got to find the IQR and then find our fences. So you need the IQR before you do your fences. Let's do that. So IQR going to equal quartile 3 minus quartile 1. Do that, you get 494.5 minus 2.5. When you subtract that, I get 242. That's my IQR. That for my next equations. So my upper fence, I mean, anything beyond this number is going to be an. Find that by doing quartile 3 plus 1.5. 1.5 is always going to be there. Okay, whenever you find your fences, your upper fence, looking for an outlier, you multiply by 1.5 times your. Here's a more advanced outlier you can find called your extreme outliers. They are really far out outliers, and those are you change that 1.5, you double it to a 3. So if something is over 3 IQRs, third quartile, it's an extreme outlier. Quartile 3 is 494.5. That to 1.5 times this IQR we found 2. Doing order of operations, I get 857.5. So off the bat, comparing my maximum to this, above the upper fence. Therefore, that's an outlier. Let's look at the lower fence to see if we have any evidence that 138 could be an. That one's kind of similar, but so that one is instead of saying your third quartile plus 1.5 times the IQR, you go to the first quartile and you subtract 1.5. The same process, just subtracting and going from the quartile. Be 252. Minus 1. Or what do we get when we do that? Okay, we get a negative $110,500 for the anything below a negative number, which can work for some problems, but not for this one. So we always kind of simplify it to 0. We don't have any home prices that are so. Because in a real world situation, you're not going to have a. Usually we just kind of flatten it out at 0. So we could say yes. The max 1,040,000. And 857, 857,000. All right, so next part of the question says a histogram of the data is as follows. So this data here is more appropriate to use the mean and standard deviation or the median and IQR to describe these data and explain. So essentially, you're either going to use the median and the IQR, distance between the first and third quartile, describe it, or you're going to use the average, the mean, and the standard deviation to talk about that data. This one or that one, one's better than the other. On this. If your data looks symmetrical, unimodal, looks like that bell curve, okay, it just naturally looks like that, then you use the mean and standard. If it doesn't, if it's literally anything else, you use the median and the IQ. This would get right, skewed left, skew it all, it's just kind of flat across, like it's not bell shaped like that, then you should use IQR. So, more appropriate to use the median IQR because it median IQR tails off this way to the wherever your tail is, like a tail, wherever your tail is, that's where this. All right. Questions. John clearly labeled this model. So it says the weights of adult male hamsters follow a normal model with a mean of 281 grams with a standard deviation of. Remember, this is going to be for a normal model our mu, which is our average. This is our sigma, which is our standard deviation. We're going to make a normal model where it's mu, sigma, right, our standard deviation. So this is going to be 281, and but we're going to start here. What this is. Adult male ham. Weights of adult male. Adult male. Weights grams. So 281. And we're going to go out 3 times. So usually where I started, where the up, up, middle, we go out 1. And then I try to find that distance, whatever. A few more. So I'm going to take this standard deviation of 8 and add it 3 times to the right. So 281 plus 8 plus 8 plus 8. And go back to the middle, the 281, and I'm going to subtract 8. 281 subtract 8, 2 subtract 8, 5 subtract 8, 7. Okay, so I have it. I have it clearly labeled. I'm going to draw like my dashed lines. By doing this, it kind of cuts up my graph into these little like strips, these little sections. So remember, this is like my 0 or 0, my z-score of 1, 2, and 3. So I start at my 0, I go out 1 standard deviation, 2 standard deviations, and 3 standard deviations. Do the same thing going to the left side, kind of. And backwards, 1 standard deviation, backwards, backwards, third. Now I'm going to make a little note that 68% of my numbers right? 8% of the numbers should fit between 73 and 89. If you buy 100 adult hamsters, okay, you should expect 68 out of 100, about that amount. Okay. Next number, 5%. Okay. So they say here to here, all that space is now 90. You get 100 adult hamsters, you would expect about 95 of them to be between 2. Lastly, I'd like to label almost 100%, but if you go out 3 standard all the way to the outside at 7 to 305, about 100, you'd expect almost 100 to be within that. Anything beyond that or less than that, you might get 1, but all right. So is it unusual for an adult male hamster to weigh as much as a female, which is 260? So it's kind of similar to the outlier type. Okay, but now this is a normal curve. We have this data. We don't have like the median and IQR and that kind of stuff. So we want to use a z-score. And generally with a z-score, we want our z-score to be like weird or unusual. It needs to either be like greater than or equal to 2 or less than or equal to -2. They're kind of loose numbers. There's kind of a lot of debate on what numbers to use. Kind of go over that later in sim. Generally 2 is that kind of that 5%. Okay, that small chance of happening. Right, if you did something and said it's a 5% chance of success, you go, wow, that's kind of a small chance of happening. That's kind of unusual if it does work out right. So it says 268 is the average female, but what if a male weighs that? Looking at this problem here, 268 would be around here. Okay, 268 would be like right between 265 and 273, so it's kind of in the middle. But let's look at the z-score. What you want to do is find the z-score for this kind of problem. We'll use 268, subtract our average divided by the standard. It is a negative, I believe it's 1.5. Okay, so because we get negative 1.625, that's not the answer, right? Negative 1.625 is not the answer for it to be unusual or usual, but with this knowledge, knowing that it's within that -2 to +2 range, right? If it's a range, then it's considered kind of average, okay? So we're going to say it's not unusual because the z-score is not past 2 standard deviation. Okay. But it's not unusual because the z-score is within 2 standard deviations from the mean, right? Last question. A machine that fills water bottles for 35 cents per gallon, and 1 gallon is 128 ounces, fills according to a normal model with a mean of 128.3 ounces and standard deviations of 0.15 ounces. Go for a second. You got a machine. It's not perfect. It does its best. It's programmed its best, but it's not perfect. This says, with some research, they found one particular machine, right, fills it up where it's a little bit extra, a little bit more than 1 perfect gallon, 128.3, a little bit of variance, right? So it kind of fills it up. And if the machine claims to fill 1 gallon of water, right, for that 35 cents, so 35 cents is more just context, not an actual problem. What percent of 1 gallon pours are filled? So 1 gallon pour under filled would be less than 128. So I'm thinking right now, on average, most of them should be about filled or a little bit extra, right? So what if you had 1 gallon and it got under? What would that look like? So what percent? And there's a few ways you can figure this out. I'm going to show you the method you should start with. Okay, get more advanced. So to start with it, I like drawing this out. Okay, in a picture. Let's draw out a normal curve, and since this is a normal model, we're going to kind of draw a sketch of this data. This is our mu, and this sigma. Whoops. That's our mu. Now when I do this, I'm actually going to write 0.3 as 0.30 because that's going to make it easier to add and subtract. Go back. All right, so remember we were drawing this out. Always. Only if you kind of follow these guidelines. Sections. Upside down parabola. This is the 128.3. 0.55. And going backwards, I got 15 and 120. Back again. 127.5. So just thinking about this for a moment. Where on this graph, right, so like this would represent the amount of pores here, pores there, whatever, all the little sections. On this graph, if this is like the 1 gallon mark, right, 128 is the 1 gallon mark, that means this little section over here is the part I care about. So if it fills less than 128, then it's underfilled. Okay, it didn't quite reach 1 full gallon. So we kind of stop right here. Thing over here, it's filled up. Okay, so generally it's going to fill up all the way. But what is that little section right there? So that's 68%. That's 95. You notice the 95% gets stopped right there. And like everything, right, out of 100%, if that's 95%, what's left over? What's left over for this piece and this piece? Well, the whole thing has to equal 100%, right? That means it's 5% left over because 100 take away 95 gives you just 5%. So it's not 5% and 5% because that would add to 105. I got to cut that in half to make that 2.5%. So that means this whole area here is 2.5%, and that leaves 2.5% for the remaining section over here, like above 126. Okay, so a few different ways you can do this. This is kind of the basic way to do it, especially if it falls right on a line. It's really easy to. So we're going to estimate the percent of 1 gallon pores that are underfilled will be that 2.5 right there. So I'd say 2.5%. 1 pores will okay. The other way to do it, I'll show you real quick, would be to just do the z-score. Okay, and the z-score would be the value that we want, which is 128. Subtract the average, which was 128.3. Divide that by the standard deviation of 0.15. And what I get is negative 2. Confirms that it's right here at that's 0, which is your mean. That negative. If you go to your book, any other resource with a, or you can just Google it. Tables that fit. Okay, so our book is a lot like the graph. Right. Over here at negative 2, which was the z-score we got 0.0228, which is kind of like about 2.28%, about 2.3%. Is that same answer we got here? No, we got 2.5 because that's just an estimation. 2.28% is actually, right, so the answer that we got was 2.5. But the actual closer answer is more like 2.2. But for a question like this, either answer would be correct. Okay, since this is more the common, easier way to do it. This way's been around for, I think I looked it up today, almost 300 years. Been doing this since like 1733, I think it was when it was developed. So this method, they say, works perfectly fine. Or exact answer, that would be 2.8%. Okay, it's literally the difference of like 22 cents, about 250 versus 228. Okay, but sometimes it might matter. In this case, we're going to say it doesn't matter. Close enough, you have a general idea what's going on. All right, so with all of that, feel free to go back and watch what you need. Email me if you have any more specific questions. Okay, hope you guys have a great, wonderful, awesome day. Guys, later. Good one.